Good morning, everyone. It's a great pleasure for me to be here. And at the outset, I thank the organizers for this invitation. I'm going to talk about something quite a simple problem, an elementary, and with an what I'm going to say is something elementary. So I suppose you may be glad to look at something elementary after a full week of intense mathematics. Okay, so the question, as might be indicated already in the title, is Diophantine approximation with non-singular integral transformations. So let me, yeah. So here is the action. I should turn it here. Okay, so we are looking at the group of, not the group. It's in fact not a group. We are looking at the semi-group of non-singular transformation, integral transformations given by n times n matrices. So, and consider the natural action of this semi-group gamma on Rn. Now, it's kind of, I think, common knowledge now that if you take a vector in Rn, the orbit of gamma, the orbit of V under gamma will be dense in V, dense for any V which is not a multiple of a rational vector. If you take a rational vector, then all the coordinate, the orbit will be discrete, and in the complementary case, the orbit is dense. Now, normally, one is used to thinking of the orbits of this group, SLNZ, but notice that this is going to be bigger. And so, when the SLNZ orbit is dense, this gamma V is going to be dense. And conversely, you can see that for rational vectors, that is still going to remain discrete. So what we know about the SLNZ orbits can readily translates to this action. This here is the reference to Dani, it's 76. Okay, so a more general version of this, you can, instead of just one copy, you can take p many copies, take a Cartesian product and take the component-wise action. And now, this is a result which was again proved by, together with Rago and myself in 1980. And it tells you that the orbit of gamma, now under the component-wise action on the Cartesian product, is dense if and only if there should not be a linear combination which makes up for a non-zero vector. So you have you see that if such a linear combination is a rational vector, then the same combination will remain rational with a certain bounded denominators, and hence it will consist of certain sheets in the n-dimensional space, so that it will again not be discrete. So this is a necessary condition, and the theorem is that it is in fact also sufficient. And again, just like in the previous case, this was the theorem initially was about SL and Z, but again the same thing holds for the action of gamma, which is what I'm going to focus on now. Okay, so before I go over to see, the main objective of the talk is going to be about the about doing so every vector, starting with a vector which is not a multiple of a rational vector, you can approximate any other vector. And now the main thrust of this talk is going to be about whether you can do it effectively. So before I come to that, let me do some recapitulation of what we know. I mean, and that is for those who are looking at such a thing for the first time, it may be somewhat instructive to see it in perspective. So now In the standard theory, what has been now sort of established and mainstream, for SL and Z, the problem is tackled by using something called duality. So this orbit, if you take such a point and look at the G action instead of the SL and Z action of SL and Z, then you have the orbit GW. This is open and dense in W. It's a nice locally compact space, and you can consider the action of G on that. And okay, so for G, any G in G, if you take, this is going to talk of the point, the gamma orbit of GU in G mod U. So I'm thinking of this orbit, G orbit GW as as a homogeneous space, and look at the gamma action on that. That's what we are interested in. So gamma action on G mod U is what I would be reduced to, and this lambda orbit is dense if and only if I need to take the U orbit of the G inverse gamma, and that should be dense in G mod gamma. There is a duality between the density of of these orbits and these orbits. It's a very simple exercise in topology. So in this way, considering the gamma action on W, or especially the generic orbits, is reduced to looking at G actions on G mod lambda and understanding the dense orbits, and hopefully one is able to translate everything back to via duality for the gamma action. Now, this lambda, as you know, is a lattice. In other words, G mod gamma admits a finite G invariant measure, and there have been dynamical studies of these kind of objects. And let's in fact say that this particular U is actually so first of all, in the result that I mentioned, also, it is partly here the result, the proof is by a combination of the duality together with some concrete work with the orbits, and so the U orbits of on G mod gamma are studied, and then it's applied to get the result. More generally, actually, for horospherical subgroups, there is also a study. Some results were proved for orbit closures of these actions, and as you would all, most of you would recognize, this sort of is subsumed now by Ratner's theory, which I'll quickly recall for recapitulation. Okay, so Ratner's theorem tells you that this is not the most general theorem, but to get a preview of what we have to say. So let G be a connected Lie group and lambda be a lattice in G. U a connected subgroup generated by unipotent elements, and now you are looking at the orbit of X, any X in G mod gamma, let's say in the form G lambda, then there exists, the orbit closure is given by an orbit of a single orbit of a larger, possibly larger subgroup. So there exists a closed subgroup F such that Fx is closed and admits a finite F invariant measure. So this sort of restricts to a particular class of groups, and the closure is an orbit of one of these. So this kind of framework generally tells you about which orbits are going to be dense. All that you need to check is that there is no such subgroup that is proper subgroup for which this can hold. Okay, so Ux will be dense if there is no proper closed subgroup F, proper subgroup F which contains G for which this condition holds. So long as you can confirm that, which you can do in many cases, though not all cases, there's still work that needs to be done sometimes, but there's a general strategy which is now used effectively, fruitfully in many contexts. Now, the point to be kept borne in mind is that these results are not effective. What do we mean by that? So it means that now you have an orbit V, let's say gamma V dense. So given implies given W, there exists a sequence gamma I such that gamma I V tends to W. So this is it tells you existence of such a sequence. But if you wish to find such a sequence, how far you have to go, what will be the sizes of gamma I is not something that is inbuilt in these results. So so for results to be effective, you need to know how something about finding gamma i's with some bounds that's needed. Okay. And there are now the rest of the talk is mostly going to be about effective results. One of the simplest and okay, here is an effective result. This is due to Michel Laurent and Arnaldo Nogueira. This is from 2012. So the whole theory that we're talking about is not very old. So this is about SL2Z, and look at a vector which is not which has irrational slope, which means it's equivalently it's not a multiple of a rational vector. Then the following statements hold. So there exist infinitely many gamma in gamma such that gamma on V is at most norm of V times norm of gamma inverse. Okay, so here notice that this sort of really stands for gamma V minus 0. So this talks is about approximating. So gamma orbit is dense. So there is a sequence gamma I going to 0, and those gamma i's you can find with the condition that the norm of gamma V is not bounded by this thing. So if you wish to have an approximation of the order of epsilon, if you want to make this less than epsilon, then gamma needs to be only of the order of 1 over epsilon. You don't have to go beyond that. Okay, so for now consider in place of 0, you consider now approximation of a rational vector. Then the result tells you that you can find gamma such that gamma V minus W is less than or equal to some C times norm gamma raised to minus half. Instead of minus 1, for this you would have minus half, and so there exists such a constant. In other words, so given the vector, there exists a constant such that you can find gammas infinitely many gammas. So that will may enable you to make this smaller and smaller, as small as you wish, and so long as and you can have gammas for which this holds. Let's say, I mean, it should be clear what it means. Now consider the general case where W is also a vector of irrational slope. Then there exists a constant. Again, this I emphasize that it is computable in terms of V and W, such that again for infinitely many gammas, here you have gamma V minus W is less than or equal to gamma raised to minus 1/3. So for the generic case, it is less effective than the rational case. Okay, so here is a word about the techniques. So the proof of the theorem of Laurent and Noguera is based on methods of continued fractions. So the okay, I think most of you, many of you would probably be familiar with the connection between the SL2Z action and continued fractions, and this can be has been used very fruitfully in many contexts, and in particular in this result. And but the disadvantage with this technique is that it is not amenable to generalization to higher dimensions. Though there is a certain amount of theory for continued fractions in higher dimensions, it's not quite useful in these kind of questions. Now, to this general question, there have also been other approaches. There's the work of Duby-Kelmer and Francois Mocoran and Mocoran and Barak Weiss. So they have proved similar results for the group is SL2R, but the lattice need not be this. You take a more general lattice and you can ask a similar question. You can ask how large the gamma is required to be to attain a certain degree of approximation. And so in the general case of lattices in SL2R. And however, in the case, if you apply those results to in the particular case of SL2Z, they're substantially weaker than what you have from Laurent and Noguera. So, and there are also results of Anish, Ghosh and Alex. Sorry? Can't hear. No, missing No, I don't follow. It's me, Alex, and Amos. Alex and? Amos. Amos, I see, okay. Amos Nevo, yeah. I'm sorry, Anish points out that there's a name is missing here of Amos Nevo. I'm sorry, Amos, for the error. So this is there are also results of Ghosh, Gorodnik, and Amos Nevo, the third missing name here, dealing with these general questions. And these are for more general varieties and not the linear case that I've talked about. So the theorem of Laurent and Noguera is also the setting being general, they are of course not optimal, and one would not expect them to be optimal given the general techniques, etc. But even the results of Laurent and Noguera, these are not optimal with regard to the exponent. In the generic case of the rational slope. Now what we had, the relation here that we had gamma v minus w is at most constant times gamma raised to minus 1/3 should in fact be, it should be possible or should hold that hold for is expected to have any exponent there that is less than half in place of 1/3. So it's only the supremum of those possible exponents should be half. Okay. Now let me come to the action of gamma that we had. So we were trying to settle that part of this gap between the exponent arbitrarily close to half and 1/3, and we could not quite make much headway in that. So we then decided to look at something that may be similar, in which we may have better luck. And here is a theorem which is with Noguera, this is myself and Noguera, and for gamma, and this is what this will be the main result to report. So for almost all x in these p many copies, let's look at the Cartesian product of p copies. Let's call this w, and we have a vector. We have the following holds. For any y, there exists a constant c such that for any rho which is n minus p divided by p and epsilon in this, then we have there gamma such that gamma x minus y is less than epsilon with size restriction norm gamma less than constant times this constant depending on x and y times epsilon raised to minus 1 over rho. So here the conditions are written independently. If you this is a kind of crucial constant, crucial number associated with this. We'll see more about what it means. And with regard to effective approximation, what we are saying is that you can find gamma for which approximates y to the extent of epsilon, and with the size of that is not greater than constant times epsilon raised to minus 1 over rho. We noticed that we're talking about infinitely many gammas, and that has been a standard practice to look at this issue. And now let me translate this condition in terms of, so in particular, if y is not in the orbit of x, then there exists a constant c prime such that, and infinitely many gamma such that this holds. Sorry? W is R cross R? No, this Rn. So this corresponds to this result. Okay. Yeah. Okay. So so there exists infinitely many gammas such that gamma x minus y is this modified constant times gamma raised to minus rho. So when you have this, you solve this for epsilon, then epsilon is less than gamma raised to minus rho times some other constant. So this translates into this. And since when you can do this for each, since you can, if gamma x is, y is actually gamma x, then there's limited choice, but you can see that if there is no actual equality of, when this is not zero, then you can find smaller, more and more gammas for which it will hold for, so there will be infinitely many gammas for which this holds. Okay. Let's see how this compares with the case of SL2Z. So when n is 2 and p is 1, this corresponds to gamma x minus y is this constant should be this one. There's gamma raised to minus rho, where n is 2, p is 1. So this is 1, and yeah, for all you will get that this is less than constant times gamma raised to minus rho for all rho less than 1, compared to we had only 1/3 in the case of SL2Z in place of gamma. Okay. Yeah. So let me say a few things about how this is kind of put in a more general perspective, or also something about this almost all. Now, recall that, I mean, I didn't say anything about these being linearly independent, etc., which you would recognize as something needed, but the point is it's here, the statement is made only for almost all. Of course, so here, these are meant to be linearly independent implicitly, and apart from that, the condition for almost all will turn out to be actually quite explicit. You can, when it's not just existence of a set of full measure, but there's a Diophantine condition in terms of which we'll be describing the set. So that is something that I'll take up next. So consider any p tuple as before, and we define something called, we call the homogeneous exponent of x, which denoted by hx, and that is you look at, it's the infimum of u greater than 0 for which there exists a constant c such that this omega x is greater than some constant times omega raised to minus u, and this should hold for all integer matrices of size n. So you have this, I'm thinking of this as a matrix with n rows and p columns. To that, I can multiply this by any integer matrix of size n cross n. The norm of that should exceed a certain particular constant times the norm of this w raised to minus u. So there'll be look at the set of u for which this holds, and take a look at the infimum. This kind of corresponds to the exponent in the usual Diophantine theory, but here with a certain modification. So, so this number is called the homogeneous exponent of this p tuple x. Now, and we say that x is projectively very well approximable if this hx is at least n minus p by p. This again is, most of you would be familiar with the idea of, with the notion of a vector, a number or a vector, or more generally a matrix being called very well approximable, or very well approximable, etc. I'll not go into the definitions of that, but here there is a specific definition that it's project, and it indeed corresponds to the classical situations. And we say that x is projectively very well approximable if this homogeneous index is greater than n minus p by p. Now, yeah, as I mentioned, this is it's in analogy with the classical notion of very well approximable vectors or matrices, if you like, here. I mean, vectors in the more general sense. Moreover, an element of W, if you take an element of W in this form, by permutation of the rows, you can always bring such a object. I mean, it's a n cross p matrix. You can bring it to this form by permutation of rows, where xi is of size n minus p times p, and theta is a non-singular matrix. You take a non-singular block of p, put it down, arrange it to be the last p rows, and then the upper part you can write in this form. Then this is projectively very well approximable if and only if xi is very well approximable. So for the matrix xi, there is a classical notion of matrix xi now comes from here in this space, and for that there is a classical notion of when it is very well approximable, and this notion of projectively very well approximable corresponds for a matrix of this form. It corresponds to this xi being very well approximable as a matrix in the appropriate dimension. So one knows that the set of vectors that are very well approximable in a vector space in the classical sense, that's a set of zero Lebesgue measure. It's a exceptional behavior, and because of what I recalled here, it's easy to see that it will mean that the set of projectively very well approximable elements is also will be of zero measure in W. So that satisfying this condition is a certain exceptional behavior. Okay, so now the relevance of this for me is that the genericity condition for that we could have the effective approximation for almost all involved two things. Firstly, as I recalled, that we should have linear independence, and secondly, that should not be projectively well approximable. If you have a vector matrix satisfying these two conditions, then that the conclusion is given. It's not the form, almost all, as was stated there in the first statement, corresponds exactly these two components. Now, the theorem is in fact proved not just for the matrices satisfying this condition that it is not projectively very well approximable. It's actually in terms of the homogeneous exponent. So the theorem is proved in a more general form with a condition on rho in terms of the homogeneous exponent of x. I will not go into the precise details. So given the homogeneous exponent, then you can so here I have given this bound n minus p by p for rho. So, and for a general case, and it turns out that for very well, yeah, let me read it from this remark. So in terms of homogeneous exponents of x, and that reduces to the stated bound when x is not very well approximable. When it is not very well approximable, then the condition will reduce to rho less than n minus p by p, and for other matrices which are very well approximable, there's a certain bound which is a bit complicated. There will be no point in sort of reproducing that here, but there is such a bound. Provided, again, that, okay, so in terms of homogeneous, the exponent x, but again, the method, however, does not apply to, nevertheless, it's not for all n-tuples, or not even all linearly independent p-tuples, but it does not apply when the homogeneous exponent is happens to be greater than this. This is, so for those for which the exponent is between n minus p by p and this, there'll be a certain result, but beyond this, there is no, the theorem doesn't say anything. Anyway, the main focus, of course, is that this holds for all x which are linearly independent and not projectively very well approximable. So that's the key part. Okay, so yeah. Now, generally, one talks about the exponents of the action. So, let me translate this thing in terms. Let me give you the definition and translate this into what it stands for. So, given x and y in W, these are p tuples of n vectors. So, the exponent is defined to be you take all real numbers. I mean, this has to be positive anyway. Real numbers such that gamma x minus y is less than norm gamma raised to mu for infinitely many gamma. So we'll look at the kind of these numbers for which we had relations of this form and take the supremum. That is called the exponent of the pair of the action corresponding to this pair. Now, so in this case, the theorem that was proved will translate in this notation, let's say, with respect to this notion, the theorem will translate to they are linearly independent vectors. Suppose that, okay, so there is actually a more concrete statement that I have recalled here. So suppose that this in Wx raised to p and Wx raised to minus p, this is greater than 0, then for all these pairs, then for almost all y in W, Lebesgue almost all y, the exponent will be n minus p by p. So again, almost all is very specific in concrete terms, and the exponent has been a practice to talk in terms of these exponents, and I have described that this is actually going to be n minus p by p in this case. Okay, so I think I have not said that this. Now, unlike in the case of SL and Z, for the gamma that we have, so in particular the exponent of in particular, the exponent of for n equal to 2, p equal to 1, the exponent of this is equal to 1 for almost all xy, and we had if you recall, for the case of SL2Z, the corresponding statement here could only be so for SL2Z, EXY is less than or equal to half for almost all xy, and this is known, and known is greater than or equal to 1/3, and expected we expect, as I mentioned, the for all, let me go back and yeah. So in this case, I said that this in place of -1/3, you actually expect that it should work with is in place of 1/3, any exponent less than half should work. That means we expect that the EXY in the notation that I introduced, the exponent of this XY should work out to be half, whereas we actually the known result is only that it is at least 1/3. On the other hand, in the case of this gamma, we know in this case we know that it is the exponent is 1, as I said, and this is optimal. You do not expect it to be this is optimal. You do not the exponent is not expected to be bigger than big. I mean, we actually prove that the exponent cannot exceed that. So in this case, we get a complete result in as far as exponents are concerned. Now, unlike in the case of the group actions, we do not have anything like duality to fall back upon. So the technique is somewhat isolated and kind of unique, and it depends on yeah. So depends on a rather interesting result that we noted. So here is let me state what the result is. The proof of the main theorem is based on the following result. This goes back to Kneser and Birch, and we use the formulation by E. Meyer in his book on algebraic numbers or something. Anyway, so formulated by E. Meyer. So it's the following. Tells you that you take this is sort of in the realm of geometry of numbers and has nothing to do with group actions, etc. And here is the sort of proof depends on elementary harmonic analysis, and it's not Okay, so the result is the following. You take a compact subset of Rn with Lebesgue measure greater than 0, such that no 2 points of S are congruent modulo n. So a compact subset in which no 2 points are differ by non-zero integral elements. No two distinct points are congruent modulo n. Now take n be the integer which exceeding 1 over mu s. Notice that it's a compact set and no two elements are congruent modulo integers, which will tell you that this mu s has to be strictly less than 1. That's yeah, so this mu s is strictly less than 1. Take 1 over mu s and take an integer which is bigger than or equal to that. So it's at least 2. And form the set K, which is S plus S plus S n copies. Okay, so additionally, for simplicity, if you take the set to be compact, then you can simply write this as n times S. Otherwise, you have to take sums of n many, etc. But if you our sets, the sets that we use are in fact convex sets. If you take a compact convex set, then you can simply have K equal to n times S. Okay, so now such a set has a property that for each vector, the K plus V intersects S. So let's say if you take a thin set here, a compact convex set, if I multiply this, so this itself has no two elements, in particular it has no non-zero, it's convex, so I just have to say that the only non-zero, the only integer point in this is 0. You take the measure of this and take the multiple by the inverse of that. That's the, this is n times. This is S and n times S, where n equal to integer bigger than or equal to 1 over mu S. Then this set, if you translate, no matter whatever translate of it you take, that necessarily contains an integer point. That is the result. So K plus this is going to be my K. And no matter where you translate this, this contains an integer point. Okay. Sorry? Sorry? N times. No, n is any integer bigger than or equal to this, and then this set is n times S. Because of convexity, n times S is same as S plus S. Okay. Yeah. So now essentially, it should tell you the relation of that with this. So in proving this theorem, one is trying to find a gamma which is these are certain convex constraints, right? And you're trying to find a gamma satisfying these convex constraints. Now, of course, it involves work and arrangement of various things, but morally the point is that you can adjust this condition to be the compact set of this form. So, and then then because of this condition, using this condition, you can will tell you that there is some gamma for which this holds. Okay, but that gamma now is still just an integer matrix. right? We are, sorry, I didn't say, we are applying this to the matrix space, okay? So, and so we are applying this n that we have, this n you want to be the dimension of the space of n cross n matrices. So here we are applying it to n square, and so using this idea, one can get, one first gets, well, one can see that one can get a matrix, n times n integer matrix, for which this will be satisfied. But the thing is to get, sorry? Diagonal action, yeah. Component-wise action. And now the other part of this, the thing is to see, is to be able to say that in fact you can find one where the determinant is non-zero. And determinant is, you can sign, of course, is not important. You can make it positive, and for that one needs to choose the sets carefully so that so that within that K, when you translate, the determinant will remain positive. That's something that one can achieve. Now in effect, of course, along with the size, the determinant could be large, but there is a control on the size. So there is a control on the determinant, but it's not going to be, it's still going to be large. So that's the that's the thrust, and that's the general idea of the proof. Of course, there are various details that I did not go, I will not be able to go into. Another remark I have made is that along with the action on Rn, you can also think of the factor action on the torus. There are many contexts in which one considers actions on the torus. So this will be a semigroup of endomorphisms of the torus, and the result for Rn will naturally also imply the analogous statements for the torus, so analogous and obvious statements. I'll not go more into that. And okay, so I think with that, thank you for your attention.
So, questions? Not, let's thank the speaker once again.